to Math383 complex analysis, lecture 10. This is the 10-4 good buddy lecture. And so what we're going to do is talk a little bit, but not too much, about the video you were supposed to watch for today, which was on Riemann's removable singularity theorem, the cassowary viastros. And I really want to concentrate on just doing examples, doing more integrations, doing more contour integrals. This is one of the techniques from class that you just have to master. I believe on the exam, which I've told you to what level it will be open book, you will have a bunch of integrals that you need to evaluate, and you only have to choose a subset of them. So you don't have to be able to do every single one. You have to be able to get a good number of them. This is one of the things you must learn how to do. However, we will see later in the lecture that the difficult integrals that we're going to be learning how to do, if you type them into Wolfram Alpha or Mathematica, it will give you the answer. Yes?
Is there a practice test anywhere?
No, just if you're fine on the homework, look at problems in the book, go to the library, take other complex analysis books, and just try to write exams for yourself. I actually did this when I was in college. My professor gave me the final for complex, and I gave him mine. And 3 of my problems were on his exam, and a 4th he almost put on but decided was too hard. One of my problems was the Riemann hypothesis, so there was going to be a generous curve on my exam, but I was used to a school where you don't get all the problems right, and that seemed the easiest way to make sure my exam would satisfy that requirement. The exam will be take home. You will have 9 days to do it, which will include 2 weekends, so you just have to find some time to do it. So I've already sent you the instructions. All right, so the main reason I really want to talk about Riemann's removable singularity theorem today is because we're keeping score between Riemann and someone else who shall remain nameless, and this way we can help Riemann set up, get a little bit back in. We will say viastros a few times this semester, especially when we get to product formulas. All right, so the big items for today is the difference between real and complex analysis. The subjects are wildly different. Essentially, I could keep this in as a general item for every single lecture. And it's the problem of your intuition is just not good because they're just so different. The only way you might have good intuition is from a physics background, doing things with Gauss, Green, Stokes, stuff like that, those different theorems. The other thing is finding the right object to study. If you can find the right transformation, a lot of times problems become very easy. The difficulty is finding the right way to look at it. The more problems you do, the more experience you have, and the easier it is to say, this is what I should be looking at. All right, so I'm not going to go through these in great detail. This way, they're just in the notes, in the slides online, but this was from the video, that if you have a function that's holomorphic on a nice open set omega, except possibly at a point z0, then we can remove it and we can make the function well behaved. So what you should always be thinking of for your example is think of something like f of z is, z minus 2. Oh, that's a horrible, horrible choice. Why is that a horrible choice? Right, and so it's distinguish between 2's and whatnot. So let's do z minus 3 over z squared plus 9. And let's say near z equals, so I don't want z squared minus 9. What do I want? Minus 9. Near z equals 3. So when you look at this function looks bad initially near z equals 3, but then you notice, wait a minute, we have z minus 3 over z minus 3, z plus 3. Why don't we just view this as the function z plus 3? And that's essentially what's going on in situations like this. We have things blowing up like this, just remove the fact of z minus 3 from the numerator. All right. Next is the cassowary-viastros theorem. There are 3 types of singularities because of how we've defined them. So there's removable singularities where f is bounded near z0, so we can do something to make it holomorphic. There's pole singularities, you have like a 1 over z minus z0 to some finite power, maybe 1 over z minus z0 to the 2021. And then there's everything else. And so as long as you define things like this, then you're quite fine. The question is just, what is this everything else? And so something that you should think of for this, for example, consider the function e to the 1 over z. If we look at a function like this, and what point would we want to look at this near? So what would be the interesting point?
0.
0. So near. So if you try to do a Taylor series expansion to this, well, we know the expansion of e to the u is just the sum of u to the n over n factorial. If we just naively expanded this, would that Taylor series converge? The sum n goes from 0 to infinity of 1 over n factorial 1 over z to the n with z not equal to 0. Does that series converge if z is not 0? Yes or no? Yeah. The expansion for e to the x converges for any x. So as long as z is not 0, 1 over z is just a number. It's growing polynomially. N factorial, boy, does that grow. Right? That's like n to the n, e to the minus n, square root of 2 pi n. This converges as long as z is not equal to 0. And what you see is that the behavior is incredibly shocking near an essential singularity. So the image is dense in the complex plane. And we're not going to talk too much about this. If people are looking for a project to do for this class to push yourself a little bit, the Picard theorem is a great thing to do. Extra credit, cultural extra credit right now. What math does Picard mention in Star Trek Next Generation that I would care about? And does he mention it correctly? You are correct. The second part is no, good logic. And the first part? Nope.
Complex.
Nope. He mentions that problems like Fermat's last theorem have been open for centuries. And with all the great things we can do technologically, isn't it amazing that something like this is still open? Well, unfortunately, that episode was done before Wiles' proof. And so they had to fix this. And so in Star Trek Deep Space Nine, they actually have a line where one of the scientists is talking with people and they say, the approach that one of your previous hosts had was the most original since Wiles' original proof. Yeah. So they at least fixed the Star Trek timeline that Fermat is known to be true then. But the Picard theorem about if you omit a certain number of points, then your function has to be constant is absolutely amazing. And the number of points depends on whether or not you are looking at the 1-point compactification, where you're including the point of infinity or not. But to be safe, if you miss 4 values of the complex numbers, your function has to be constant. And you can lower it from 4. If anybody's looking for a good thing to look up and present to the class as a project, the Picard theorem is a great one to do. There's big Picard and little Picard. There is also the Jordan plane curve theorem. These are great things if you want to do some presentations. I sent an email recently about people needing letters of recommendation, and somebody was asking me who never had me in a class and never had an opportunity other than just my advising them on the equilibrium. If you're looking for letters of recommendation, this is a great thing you can do, learning some deep material like this and presenting it to the class. All right, and so this is just the 1-point compactification. This image is, of course, drawn from the book. The idea going on in a situation like this is that there's 1 point at infinity. And this is doing the stereographic projection where we can put points in the plane to 1-to-1 correspondence with points on the sphere. And all the points going off to infinity go to the North Pole. And some people have a little trouble saying that there's only 1 point at infinity because there's so many different ways I can go to infinity. But if you consider the map z goes to 1 over z, then all the points going near 0 spread out to going all the different ways to infinity. And so when you look at this, what you do is you draw a line from the North Pole, it hits the sphere, and then it continues on, say it hits the plane. And so you could say like the points in the southern hemisphere correspond to the points inside the unit circle. The points on the boundary just stay where they are. And the points in the northern hemisphere are the points coming from outside the unit circle in the complex plane. So you can basically do this kind of mapping from the complex plane to the sphere. So you take this infinite plane and you're now mapping it to a sphere, which is absolutely wonderful. The difficulty, of course, is that you don't have the North Pole. Well, what should the North Pole correspond to? If you look at limiting of what's going on, it's going to correspond to all the points at infinity. And this is called the 1-point compactification, and this is the Riemann sphere. And so Riemann at least gets another mention over here. So I would draw things a little bit differently. I would have drawn the plane a little bit higher up going through the equator. And so for me, it looks like they might be using 0 as maybe the origin. I would have it as the South Pole. And if it was me, I would draw my plane like this. And then here's the unit circle. And then you would draw the sphere coming up as well as the sphere going below. And so when you do it like that, anything inside the unit circle, goes to the southern hemisphere. And then anything outside goes to the northern hemisphere. Okay. Yes, so everything, as you get further and further away from the origin, that all is going to go to the North Pole. Just like if you think about what's going on, if you take a point that's going further and further away, if you take the mapping z goes to 1 over z, as you go off to infinity, when you do 1 over z, you're now heading towards 0. And you're all heading towards one point. So all the points at infinity are really collapsing to one common point, the origin. Okay, so what I want to do now is I want to spend the time talking about doing certain types of integrals using contours, introduce some new techniques, show you how we can handle a variety of functions, and give you some idea of how sites like Mathematica actually work and compute stuff like this. How many people have used Mathematica a lot? How many of you know how to use assumptions in Mathematica? Okay, so I'll show you a little bit of how to do that. You can help Mathematica a little bit by trying to tell it, when I want you to do this integral, this parameter has values in this range. And that is often important because if the value is outside that range, the integral may not exist. And so if you can help guide Mathematica in doing these calculations, this is very valuable. Again, there is a difference between what I was taught and what you were taught. I am not as bad as what I'm about to pull out, I think, yes. So what am I about to pull out? A slide rule, okay? Extra credit for anybody who has a slide rule. No, so if you have a slide rule, show it to me, bring it to me, and you will get extra credit. Then you decided poorly. If there is a nuclear blast and the electromagnetic radiation fries everything. So I have that slide rule. These ones were gifts from family members. I have the circular slide rule, which if you've never seen is absolutely wonderful. I think it's much better to the regular one. And I have one other slide rule, but I think I might have left it at home as I was lightening my bag for the trip. And so a lot of the technology has become obsolete. And so it is interesting as to what do we have and why. So slide rules were extremely valuable for long periods of time. I think I left it home to minimize my bag. Slide rules are extremely valuable in the old days, but now with computers, you don't really use slide rules that often. I learned how to do integration using tables of integrals, and it was a lot of work to convert what you have to something that fit the table of integrals. So today what I want to do is talk a little bit about how to do certain types of contour integrals, and then let's convert various things to match what we have. So the first is I want to talk about some things from probability. The expected value of e to the tx versus e to the itx. And so the first one is called the moment generating function. And the second one is called the characteristic function. Is there much of a difference between them? No. If I just replace t with I times t, I can get from one to the other. So why do these matter? So let's say I have a random variable x with density f. And if you have more functions in play, you might do f sub x to remind you that this is the density coming from the random variable x. So this means the probability that x takes on a value between a and b is just the integral from a to b of f of x dx. So the expected value of some function of x is just defined as the integral from minus infinity to infinity of g of x f of x dx. Certain functions are easier to work with than others. Certain functions are more useful to look at than others. So the first that we want to look at is the generating function. So this is going to be the expected value of e to the tx. So this means I have to integrate from minus infinity to infinity of e to the tx f of x dx. Okay. Any thoughts as to how we might do this integral? So let me introduce moments. Well, I'm going to let the kth moment be the integral from minus infinity to infinity of x to the k f of x dx. So this is the kth moment. If you want, the hope is that if I understand the moments of my distribution, I understand the distribution. This is similar to the hope we had that if we understand the coefficients in the Taylor series, we understand the function. Our hopes were dashed there, our hopes will be dashed here as well. We'll get used to it. But it's still not a bad thing to try. And the hope is that, well, maybe if I have some additional conditions, the Taylor coefficients will uniquely determine my function. Maybe if I have some additional conditions, the moments will determine my function. And then we just have to find out what are those technical conditions, or equivalently, what subspace do we have to restrict to? So the idea is if I understand the moments, hopefully I understand my distribution. So I have the integral of e to the tx. When you see e to the tx, what do you think of? When you see e to the tx, Taylor series. So this is just going to be the integral from minus infinity to infinity of the sum, and goes from 0 to infinity, of t to the n, x to the n, over n factorial, f of x dx. And now there should be something that you should obviously do if you're not a math major. And if you're a math major, there's something you should do, but only with great trepidation. Yes. And so explicitly, switch the order of summation in the integral. Right? So you need some type of Fubini theorem, Fubini Tonelli, that says we can switch the order. This is really your product measure. And so if you take absolute values and everything is finite, then you can switch. So not worrying about that. This is the same as the sum, n goes from 0 to infinity. We have t to the n over n factorial coming out, and we have the integral from minus infinity to infinity, x to the n, f of x dx. But what is the integral of x to the n, f of x dx? X to the n plus 1 over n. No, because we have x to the n times f of x. So we're trying to do that entire integral.
Just a moment.
Yeah, just a moment. Which moment?
mu1.
Yeah, mu1. And so this is just going to be the sum, n goes from 0 to infinity, of mu(n) over n factorial t to the n. Hence the name. The coefficients of this are the moments. And this is why it's called the moment generating function. When you expand out e to the tx, when you calculate its Taylor series, its coefficients are essentially the moments. So this is wonderful. If I'm trying to understand something from probability, I now have a function where the Taylor coefficients are the moments. So we need the Fubini Tonelli theorem. So if the integral of the sum of the absolute values is finite, then can switch. And so if you look at this, you have to show that you are in a situation where if you put in absolute values, that everything will converge. it's not going to always be true. So this is not always true. I'm not saying it's true in this case. I'm just saying I did it. Right? You need to prove that the moment generating function exists. So does not exist for all densities. So just because I wrote this down doesn't mean I can always justify it. So can anybody give me a probability distribution where this probably won't work? Yeah, Cauchy distribution. And so, Riemann was getting some points earlier for the Riemann sphere, which was not directly related to a lot of the complex. And now Cauchy is getting some points for the Cauchy distribution from probability, the 1/1 plus x squared. You can argue as to whether or not that has a mean. It's symmetric about the origin, so you can at least say, it looks like it has mean 0. It doesn't have higher moments. And so if the moments don't exist, clearly you're going to have trouble here. Well, let's look at some other functions. For example, let's consider f of x equals e to the negative x if x is greater than or equal to 0, and 0 if x is less than 0. So is this a probability distribution? Does this integrate to 1? Is it non-negative? Yeah. So integrates to 1. Is non-negative. Let's try to calculate the moment generating function. So that's going to be the integral from -infinity to infinity of e to the tx, e to the negative x dx. So this is the integral from -infinity to infinity of e to the negative 1 minus t of x dx. I did that correctly. What does that integral equal? Yes. So what should the bounds of integration be? Yeah, it should be from 0 to infinity, because our function is defined to be 0 outside. Thank you. So what would this integral be? One nice way to handle it is this is equal to 1/1 minus t integral 0 to infinity e to the negative 1 minus tx times 1 minus t dx. So if I let u equal 1 minus t, what would du be? Oh, so 1 minus tx. Then du would be 1 minus t dx. And this would just be 1/1 minus t equals 0 to infinity e to the minus u du, which is just 1/1 minus t. Is there anything I have to be careful about? I'm sorry? So if u is negative, it blows up. And so what must be true about t? So what do I need to be true about t? So we need 1 minus t to be greater than 0 for the integral to make sense. Right? So that means we need t to be less than 1. So here the moment generating function exists, but not for all t. So the moment generating function exists for some, but not all t. If we consider, f of x is 1/1 plus x squared, then the expected value of e to the tx would be the integral from -infinity to infinity of e to the tx over 1 plus x squared dx. So I don't care if t is positive or negative. If t is positive, look at positive x, it blows up. If t is negative, look at negative x, it blows up. There's only one value of t where this is defined. What value of t is this defined? 0. So if t equals 0, it's okay. We get pi. If t does not equal 0, we have exponential growth, undefined. So the problem is the moment generating function does not always exist. So when you're trying to do probability, it's a very useful thing to look at because the moments are built into it. And this is why we study the characteristic function. So this is the expected value of e to the I tx. So it'd be the integral from minus infinity to infinity of e to the I tx f of x dx. Morally, what does this look like? Up to an accent, what is this? Yeah, so up to an accent, it is the Fourier transform. Right? So then the question becomes, which Fourier transform do you want to define? Do you want to have it as e to the I tx, e to the 2 pi I tx, e to the negative 2 pi I tx? Do you want to have square roots of 2 pi outside or not? But it's essentially a Fourier transform. I can always adjust those constants without a big deal. Now, we talked about how the characteristic function is similar to the moment generating function. The difference is the I. What's nice is this always exists. And the reason it always exists is if we look at the absolute value of the integral from minus infinity to infinity of e to the I tx f of x dx, this is less than or equal to the integral from minus infinity to infinity of the absolute value. But since f of x is a probability distribution, what do you know about f of x? We know its integral is 1, but we know something about the density. So what's true about probabilities of events? Positive or a little bit weaker than positive. What's slightly weaker than positive? Non-negative. So my function f can't be negative anywhere. So the absolute value of f is the same as f. What about e to the I tx? What do you know about the absolute value of e to the I tx? It's just 1. So this is just the integral of f of x dx. And now we use the fact that you said that it integrates to 1 to just say, oh, that this integral is 1. So the Fourier transform or the characteristic function always exists. That is a huge advantage over the moment generating function, which does not always exist. It's better to work with objects that exist than to try to work with objects that do not exist. And this is why in proving a lot of results in probability, we love to switch to the complex plane. So even though we're talking about real probabilities, we move to the complex plane. And there's a great quote that often the shortest path between two truths in real analysis is through the complex plane. There's lots of different ways of formulating this. But when we get to the prime number theorem, counting how many primes there are, we're counting integers. We're counting subsets of integers. Why should we be going into the complex plane? Because complex analysis gives us incredibly powerful tools. And so we want to use them. And so this is just motivation for what we're going to be doing as to why we're considering the contours we're considering, why we're considering the functions we're considering. One of the big applications of this subject is to probability. And we'd love to be able to prove things like the central limit theorem. To do that, it would be great to use the moment generating function, but the moment generating function doesn't always exist, but the characteristic function does. And so this is motivation for considering the following integral, the integral of e to the I tx over x squared plus 1. So this is essentially the Fourier transform of the Cauchy. So essentially the Fourier transform of the coshate. Okay. So the first thing we need to do is we need to figure out what function do we want to look at and what contour do we want to do. Well, I've put the contour over here. You have to decide, do I want to be doing a contour that goes up or goes down? The function here, what do you want to choose for your f of z? You have, I think, two choices. So we need to complexify the integrand. Yes.
Change every x to the z.
Change every x to the z, right? E to the iz over z squared plus 1. Or what else could we do? But we're integrating over x, so we can't just change some of the x's. Yes.
Change everything with a minus z.
No, no, not gonna let that. Nope. I'm sorry? Oh, the pen must have shifted to right for a moment. Thank you. There is another choice we can do. Yes. No. That is the same, because it's the same function. It's just written differently. So the other thing we could do, does it help if I write the letter C? Yes. So I could write it as cosine tz over z squared plus 1. And the reason is if I write this as e to the I tx as cosine tx plus I sine tx, the sine tx is going to be odd. And so when I divide by x squared plus 1, it stays odd. And so the integral of the sine part is just 0. So I can just throw that away. So I could look at either one of them. It's good to look at e to the I zt over z squared plus 1. And let's think about what's going on. So if t is greater than 0, e to the I zt is going to be e to the I xt e to the minus yt with z equals x plus iy. And now if we look at what's going on, e to the minus yt, if t is positive, as y gets larger, you have exponential decay. So as you go further and further away from the real line, you get more and more decay. So this is a good contour to use if t is greater than 0. If t was less than 0, this would be a bad choice, right? Because if t was greater than 0, I'm sorry, if t was less than 0, things would become exponentially growing. So what would you do if t was less than 0? I'm sorry? So one is to use the lower semicircle, or the other is to say, let me just replace t with negative t. Because if you look at this, this is where looking at it as cosine of tz over z squared plus 1 is useful. If I just replace t with negative t, I don't change the value of the integral. And so I can always reduce myself to the case that t is greater than 0. So can reduce to case t is greater than 0 by sending t to negative t. That's written terribly. T to negative t if t is less than 0. So if we're in a situation where t is less than 0, I could just change things and just assume. But again, before we do these calculations, you always want to think about what are the values of the parameters. So we are going to be studying this in the special case when t is greater than 0. So we will analyze when t is greater than 0 and have exponential decay as move up. All right, so now we just have to figure out where is the integrand bad? Where does it have poles? Well, we have z squared plus 1. We've seen this before. So if we have e to the I tz over z squared plus 1, we can write this as e to the I tz over z plus I times 1 over z minus I. And I'm using z squared plus 1 is z plus I times z minus I. And so when I want to calculate things, I want to find what is the pole. So there are two poles. There's the pole at I and negative I, but only one pole is inside the region. The only pole that matters is z equals I. And we just have to figure out what is the residue. This is the simplest situation we can be in. And the reason is 1 over z minus I, we only care about the negative first term in the Taylor expansion. We only care about what's going on at the 1 over z minus I. If you look at e to the I t z over z plus I, this is holomorphic near I, right? So this is holomorphic near z equals I. So this is going to have residue e to the I t I over I plus I, or that's e to the negative t over 2I. Does everyone see how we got that? And so the result we're using the following. Let's say we have a function a of z is b of z times 1 over z minus z naught, with b holomorphic at z naught. Then we can write b of z as maybe say b naught plus b1 z minus z naught plus b2 z minus z naught squared. You know, because it's holomorphic, it's analytic. And so when we look at b of z times 1 over z minus z naught, we get b naught over z minus z naught plus b1 plus b2 z minus z naught plus dot dot dot. And so here we see the residue is just b naught. If we had things a little bit more general, if instead of having 1 over z minus z naught, if I had 1 over z minus z naught squared, what term would matter? So if we had a of z was b of z times 1 over z minus z naught squared, then the residue is what? It would just be b1. So we can figure out the residue very simply if we can write our function as a product of two functions, where one has all the terms that blow up. And then what if we had, say, a of z equals, b of z times 1 over z minus z naught plus 3 over z minus z naught squared. What's the residue? Yeah, it'd just be b of 0 plus 3b1. So general rule, break a complicated object into a bunch of simple ones. For each simple one, figure things out, and then put them all together. Okay, so now that we have this, let's turn back to the integration. So we want to integrate from minus infinity to infinity, e to the I tx over x squared plus 1. So we convert this to integrating from minus r to r of e to the I tx over x squared plus 1 plus the integral over the semicircle. I have a 1 over 2 pi I by each one of these. And then we'll have an e to the I tz over z squared plus 1. And then that equals the sum of the residues. And what was the residue? I think we had it was e to the negative t over 2i. So we get e to the negative t over 2i. Okay? So we're just doing the contour integral. And then we take the limit as r goes to infinity. The first piece is going to become what we want. And then we need to just show that the second piece is negligible. So why is this small? The absolute value of e to the I t z over z squared plus 1 on this semicircle is going to be less than or equal to e to the minus yt over r squared minus 1. Right? Because we're on the semicircle. We have a lot of exponential decay. We have e to the minus yt. This is really good decay as long as we move a little bit away from the x-axis. So if we're near the x-axis, it might not be great. As we move away from the x-axis, it has good decay. But worst case for us in the bottom is if z squared is negative. So we're basically right at the point 0 plus ir. So it's at least r squared minus 1. Oh, sorry, at most r squared minus 1. So the contribution in absolute value is going to be less than or equal to 2 pi r times e to the minus yt over r squared minus 1, and this goes to 0. So when we put all the pieces together and we multiply by 2 pi I, we get that the integral from minus infinity to infinity of e to the itx over x squared plus 1 dx. So we multiply by 2 pi I, the 2i cancels, we get, I believe, pi e to the minus t. So the first thing you should do is check, is this reasonable? Can you think of any checks to do to see if this is reasonable? Yes.
See what happens when t is equal to 0?
So you could try when t equals 0. Excellent. So 1, if t equals 0, we get pi. That's good. We know that. Good. What else could we check? We know the integral of 1 over x squared plus 1 is pi. We've done this integral before. We can use arctangent. We can use contours. What kind of number should this integral be? What kind of number should it be?
Real.
Should be real. Is it real? So 2, it is real. Now, a little bit harder is it should actually be positive. And the reason it should be positive is when you look at cosine, cosine can be positive and negative, but it starts at positive, becomes negative, becomes positive. X squared plus 1 is decreasing. So if you look at it, it starts off with the larger values when everything is positive, then you have the negative values, and then you have positive values again. And so with a little bit more work, you can actually see should be positive. So this passes all the different smell tests. And it's wonderful that you can do something like that. Okay. But again, if you can do these checks, these are really good to see, have I made a mistake somewhere? Have I dropped the 2 pi I? Have I forgotten a residue? Really nice to do. All right. So what I want to end with is how you can evaluate some trig functions. So let's say we want to integrate d theta over a plus cosine b. I could have done, could do the integral from 0 to 2 pi of d theta over, say, alpha plus beta cosine theta. Why am I not doing alpha plus beta cosine theta? Why do I say it's enough to consider the special case when beta equals 1? Yes. Yeah, exactly. I can just pull out the beta, and this is going to be the same as, d theta over, I can write alpha as alpha times beta over beta. So it's just going to be alpha over beta plus cosine theta, integral from 0 to 2 pi, and I pulled out a beta. So it's enough to handle the special case. So anything you can do to try to simplify life, I might as well assume I just have a plus a cosine theta. What do I want to assume about A? I want this integral to be nice. What might you want to assume about A? Yes?
The absolute value of A is greater than 1.
Yeah, if we assume the absolute value of A is greater than 1, so the denominator is never 0. And in this way, at least we're not integrating with a, it's blowing up on the line of integration. So if you feed this into Mathematica, it generates out this gobbledygook, the flow of negative argument of, it's absolutely wonderful. Then you can, hold Mathematica's hand and tell it, look, assume A is greater than 1, because if A is negative, we can probably play some games and maybe cancel that. I don't know. Maybe no, negative A we might not be able to do. Can we? And then just assuming that A is real, and then we can get a really nice answer like that. And then for fun, could we actually do cosine squared? And actually, yes, we can get the integral of cosine squared as well. So looking at the claimed answer, it looks like it doesn't matter if A is greater than 1 or less than -1 in real, they give the same answer. So there should be some nice, transformation that allows us to go from A to -A. Yeah, I was about to say probably just shift theta by a fixed amount, and then that would shift cosine and pull up a -1. So that gives you good ways to check and see this. All right, so why is this in complex analysis? Well, we want to integrate from 0 to 2 pi of d theta over a plus cosine theta. Now, cosine theta is e to the I theta plus e to the minus I theta over 2. If the absolute value of z equals 1, then we can write z as 1 times e to the I theta. So cosine theta is 1/2 z plus 1 over z. So this is true on the unit circle. So what that means is our integral equals the integral over the circle of radius 1 of d theta over a plus 1/2 z plus 1 over z. Okay, except it's no longer d theta. Right? I gotta write this carefully. What should come up there? So if z is e to the I theta, what would dz be? So e to the I theta, I d theta, right? Which is just I z d theta. Yes? We agree? So if dz is iz d theta should then just be dz divided by iz. So it should be 1 over iz dz. And so this is just 1 over, I'll bring out the 2 as well. Integral absolute value of z equals 1. We'll have a dz upstairs. And when I bring the z downstairs, I have a 2az. I'll have, I think, a z squared plus 2az plus 1. I think that's what we get when we put everything together. Yep. Because I'm pulling out the 2, so I have 2a. Do we know how to integrate this? Can you figure out how to integrate this? Yeah, we just look and see, where are the poles? Is it hard to find where z squared plus 2az plus 1 has zeros? No, what would you use? Quadratic formula. But what if a is not a real number? Can you still use the quadratic formula? Yes. Have you ever used the quadratic formula for complex a? This is your chance, right? And then you realize the algebra is just the same. And so we can use the quadratic formula. Use quadratic formula. And so for fun, what about, we'll end with this, the integral from 0 to 2 pi of a plus cosine squared of theta? Can we handle integrals like that? And if so, how? And what's the easiest way to handle them? Because there could be more than one way. So this is a good place to start, primarily because it's also 11:51. But this just shows you here is another whole class of functions we can integrate using complex analysis. But as always, remember, we're not integrating in general, we're integrating over very nice